So in this video, I want to talk about adding vectors, how do we add two vectors, and also what it means to multiply a vector by a scalar. So let's talk about adding vectors. So I'm just going to write adding. Okay, let's imagine we had two vectors here. Vector u, which looks like this, it's vector 2, 1, and then vector v, which looks like this. It's going to be -1, 2. And if I wanted to add u and v, I could write u plus v, literally like this. And then what we do is we add up their respective components into a single vector. So this would be 2, 1, that would be our u, plus v, which is -1, 2, which is going to be equal to 2 plus -1 is 2 minus 1, so that's going to be 1. 1 plus 2 is going to be 3. And this right here is u plus v. And that's how you add two vectors. It doesn't matter whether they have they're two-dimensional like this, or they're three-dimensional, fourth-dimensional, five-dimensional, 100 million dimensional. It does not matter. You add them up component-wise. Subtracting. In order to subtract two vectors, you can, and this is a nice segue into scalar multiplication. If I wanted to subtract u and v, this is the same thing as u plus -1 times v, right? And we can actually write arrows above these. You'll commonly see this to signify that they are vectors. And right here, this is just going to be 2, 1 plus -1 times -1, 2. And so here we're talking about multiplying -1 times v. This -1 is what we call a scalar. And so a scalar is just it's a scalar quantity. It's just a number that you're going to use to multiply a vector, and it actually scales it, and you'll see that in a second. But essentially what this is going to be is you take -1 and you multiply it by both of the components, and that's going to give us this 2 plus -1 times -1 is 1, -1 times 2 is -2. And then this u minus v is going to be 2 plus 1, which is 3. 1 plus -2 is 1 minus 2 is -1. And this right here, this is going to be u minus v. And so adding is really only talk about adding because, you know, if you want to subtract two vectors, you're just adding. What you would do is you take the first vector plus -1 times the next vector. And it's the same thing as subtracting. But yeah, let's talk about scalar multiplication. I'm going to draw a line right here. I can write that a little bit cleaner. Scalar multiplication. I'm going to shorthand it. And so if we have a vector, let's use u. In our case, we have u. U is 2, 1. And let's just say I want to multiply it by the number 3. And so I'm going to say our scalar is going to be 3. Well, I could write this as 3 times u, get our arrow, and that's going to be 3 times 2, 1. And that's going to be, you know, multiplying each component. That's how we multiply by a scalar. It's going to be 6, 3. And this is our new vector u. And so what if you could imagine if we were looking at, you know, u on a coordinate system, you know, it started out, I'm going to write it actually a little bit smaller. If we're looking at u on a coordinate system, it had 2 in this direction, right? So in this direction it had 2, in this direction it had 1 beforehand. And this was u. And then we multiplied it by 3, and then we got 3u. And so now what happened is that we have, you know, added up 2 3 times. We got 6 on this side, and this side on this axis, and then we have 1 here, 1 here, 1 here to get us 3. And so in this instance, if you multiply by 3, it's like taking the length, the vector itself, and stacking it up on top of itself in the same direction 3 times. And that's scalar multiplication. Interesting enough, when we multiply by -1 over here, if I was to multiply u by -1, that would be the same thing as just flipping it directly on its axis. So if we look, I can draw a better one. it would look something like this. So this would be -1 times u. It would just be flipping it, right? Because it'd go from 2, 1 to, sorry, I said that it, we did it right here, but this is v. But you get the picture. It would be -1 times 2, 1 is going to be -2, -1. And so it's going to flip it along the axis if we're imagining that we're dealing with a regular Cartesian coordinate plane here. And so that's adding, subtracting vectors as well, and scalar multiplication. So we saw how multiplying a vector by a scalar increases its length by the size of the scalar. And it can also flip it as well. And in this video, I want to hone in on how do we actually calculate the length of a vector. And once we are able to calculate a length of a vector, I want to show you how to take a vector of any length and then normalize it down to have length equal to 1, because unit vectors is what we call vectors that have length equal to 1. They're extremely important in linear algebra. So let's start off with calculating the length of a vector. So length of vector. Okay, and so let's take our vector u. U has these components. It's a two-dimensional vector. And what we want to do is we want to calculate its length. And so the length of a vector is going to be literally just the length of the vector itself, how the distance, how long it is. And so if you remember the Pythagorean theorem, let's see, that actually makes u look like is not centered at the origin. Let's imagine that u is centered at the origin. And so this is u, and it's equal to 2, 1. And so this is our x-axis, this is our y-axis, u is 2 here, and then 1 here. And we want to get the length of the vector. Well, the length of the vector is just the hypotenuse. And so imagine this does make a right triangle right here with this axis. And we know this side is equal to length 2, this side is equal to length 1, and so we want to know what c is. And if you remember because this is if this is the Pythagorean, if we're looking at this geometrically, this is a and b, and then the hypotenuse is c. And you may remember the famous equation that c squared is equal to a squared plus b squared. And so if you wanted to get we don't want c squared, we want c. And so if we wanted to get c, we would just take the square root of both of these sides. The square would go away, and then we'd be left with c is equal to a squared plus b squared, where a and b are actually the components of this vector. And so this formula right here is actually how we calculate the length of this vector. With the square root over the a squared and b squared. And so in this case, our a is 2, our b is equal to 1. And so this means our c is going to be equal to the square root of, 2 squared is 4, plus b squared, which is just 1 squared, which is 1. And this means c is equal to the square root of 5. And so this is the length of this vector. The length of this vector is the square root of 5. And so the square root of 5 is something over 2. It's a little bit over 2. But we want to be able to make this vector of length 1. So we just calculated its length, and for whatever reasons I won't get into right now, we want to make sure that this vector has length equal to 1, not length equal to square root of 5, which is a little bit over 2. And so what we're going to do is now we're going to normalize. And I'm going to write that a little bit cleaner. Normalize. And so we know that the length of u, we can actually write the length of u like this. The magnitude of u, or the length of u, is equal to the square root of 5. And we know that u is equal to this. It is 2, 1. That is our vector. And we want to get it down to have length 1. The formula for doing that is going to be u divided by its magnitude, or its length, which in this case is going to be 2, 1. Okay, divided by the square root of 5. And when you divide, take a vector and you divide it by a scalar, same thing as multiplying, you just divide each of its components. And so, this is the same thing as 1 over the square root of 5 times 2, 1, which is also, if you distribute it through, is the same thing as 2 over the square root of 5, 1 over the square root of 5. And if you were to take this vector and then calculate its length, how we did over here, by plugging in a is equal to 2 over the square root of 5, b is equal to 1 over the square root of 5 into this formula, you will see that the length of this vector is equal to 1. And so that is how you actually calculate the length of the vector. So we took a vector u, right? We calculated its length, and we said its length is the square root of 5. And then we said, well, we don't want it to be the square root of 5. We want it to be equal to 1 because, for reasons that we won't go into, working with the unit vectors is a whole lot easier in a lot of cases. And so that's what it means to have a length 1. A vector have a length 1 is going to be a unit vector. And so we said we could do that by taking u and dividing it by its length. And so we went through those steps, and then now we got u normalized, or have a length 1, or it's a unit vector, and these are its components. And so I encourage you to go through the exercise of actually computing the length of this vector over here just to confirm that it is length 1. So we've talked about adding two vectors and how we would subtract them as well. In this video, I want to talk about how to compute the dot product between two vectors. And after we learn how to do the dot product, I think it's going to be a good idea for us to go through how to multiply two matrices. And we're going to talk about what a matrix is as well. So let's first start off with the dot product. Let's dot. I can write that a little bit better. Dot product. Okay, and so let's start off with our vectors u. And let's do v, and let's make v this time be like -2 and 3. And so if I can write the dot product like this, I can say the dot product between u and v with this little dot is going to be equal to u transposed times v. Now u transposed, if I was to transpose a vector, if my vector had dimensions 2, 1 in this case, after I transposed it, it would have dimensions 1, 2. And so u transpose is going to look like this. It's going to be 2, 1, 1 row, 2 columns, times -2, 3. And what you do when you do the dot product is you take this component times this component. And so the first component of the first vector times the top component of the second vector. And that's going to be -4. You take this component times this component, last component of the first vector times the bottom component of the second vector. In our case, if this was 3 dimensions, you would just make sure that they match up accordingly. And this can be 1 times 3, and you add them together. And so -4 plus 3 in this case is going to be -1. And this is the dot product between these two vectors. And so since we know about the dot product, let's talk about matrix multiplication and what a matrix is. So we've talked about vectors, right? But let's imagine that, let's talk about a matrix. A matrix, let's imagine that we took these vectors and we put them into a matrix where each column of this matrix was one of these vectors. So you can see right here we have u, right here we have v. And a matrix is just a little bit different than a vector. When we refer to something as a matrix, we're commonly referring to something that has more than one row and more than one column. It's commonly how you'll see it referred to. And so this is a matrix, and if I wanted to multiply this matrix with another matrix, let's say b, and let's say b is like 0, 2, 3, -1. The matrix multiplication between a and b would go like this. So if I had a, I'm going to bring a down. And I'm going to bring b here, 0, 3, 2, -1. Since you're kind of, you're kind of aware now of how this relationship of a vector being transposed and then multiplied by each respective components this is how matrix multiplication is actually going to work. If I have a 2 by 2 matrix and a 2 by 2 matrix, this the output matrix that we get is going to have the number of rows of the first matrix, and the number of columns that it'll have would be the number of columns of the second matrix. And so, for example, if A was actually 2 by 3 and B was actually a 3 by 4, then the output matrix would be a 2 by 4. And you'll see kind of soon, as you work through these examples, you'll see how that sort of comes to be. But first and foremost, this first cell up here, this is going to be a 2 by 2 matrix. And this first cell up here is going to be this vector dotted with this vector. So dot product between these two vectors. And that's going to be 2 times 0, which is 0, plus negative 2 times 2, which is negative 4. I'll keep the plus sign. Then we're going to do this vector dotted with this vector, and then that's going to go here. And that's going to be 2 times 3 is 6, negative 2 times negative 1 is going to be 2, and then we're going to have this vector times this vector, and that's going to be 1 times 0 is 0, 3 times 2 is 6, and then we have 1 times 3 over here, plus or minus 3. We'll keep the minus this time, because 3 times negative 1 is negative 3. And then we just sort of, do our adding. We have negative 4 up top right there in the top left. We have 8 right here, 6 right here, and 0 right here. And this is the matrix multiplication between A and B. It has dimensions 2 by 2. And so that's the key things to remember. The multiplication of two matrices A and B, the resulting matrix, you can call it C, is going to have the same number of rows as A and the same number of columns as B. One key fact, must have for matrix multiplication. If A was a 2 by 3 and then B was a 4 by 2, this would not work. The inner dimensions here, they must be the same. And think about it, right? If A was a 2 by 3, that means you would be taking a 3-dimensional row vector right here, and then taking the dot product of that with a 4-dimensional column vector. And that wouldn't match up because you have to do component by component multiplication like we did over here, 2 times this, 1 times this, and there's a mismatch between the number of components, and so that cannot work. And so that's a very important property of matrix multiplication. Always make sure that your dimensions match up. And so that's the dot product, and that is how to multiply two matrices. In this video, we're going to talk about what a determinant is. How do I calculate the determinant of a matrix, since we know what a matrix is? And we're also going to talk about how to compute the inverse of a 2 by 2 matrix. We won't go into the 3 by 3 case, and we'll utilize the determinant of this matrix that we calculated. And so let's imagine we had this matrix A, and A was 2, 1, 3, 4. Write this 4 again. And this is a 2 by 2 matrix. And so first, I want to calculate the determinant of A. And so I'm actually going to write it like this, the determinant of A. And I can write this like this. You'll commonly see, I'm going to write that a little bit straighter. You'll commonly see people put the matrix in between bars like this. And how do you calculate the determinant of a 2 by 2 matrix is you multiply the right going diagonals by each other, so 2 times 4, and then you multiply the actually this would be the left to top right diagonal by itself, by each other, and then you subtract them off. And so this is going to be 8 minus 3, and the determinant of this matrix is going to be equal to 5. Now, to go into a segue into how do we actually calculate the inverse of A, I can write a straighter line. I can do it 3rd time's the charm. This is going to be, you can commonly see this signified as A inverse with a superscript -1, and this is going to be 2, 3, 1, 4 inverse. And so the inverse of a 2 by 2 matrix utilizes the determinant. The inverse is going to be 1 over the determinant, which is 5 in this case, multiplied by, what we're going to do is we're going to swap these two. So it's going to be 4 and 2, and then we're going to negate these two by multiplying them both by -1, but keeping them in their original spots. Make sure they're separated, okay? And then we just distribute 1 over 5 through the matrix. 4 over 5, -3 over 5, -1 over 5, and then 2 over 5. And then this right here is the inverse of A. And so that, quite simply, that is exactly how you take the determinant of a 2 by 2 matrix. That's how you calculate the inverse of a 2 by 2 matrix, and it's incredibly straightforward. In this video, I want to explain what a system of linear equations is. And so we're going to do that through an example. And so I'm going to write out a system of linear equations. It's going to be a system of 2 linear equations. This is going to be our first one, and then our next one is going to be this one. Alrighty. And so a little refresher on what a linear equation is going to be helpful, because then it's going to be really easy to understand what a system of linear equations is. But here I'm going to give you some grid points just to help. And so a linear equation, let's look at this one right here, and let's plot this linear equation. What we can do is we can rearrange this equation and solve for y. And so if I solve for y here, I can, subtract 2x to the other side. That's going to leave me with 8 minus 2x. I can divide through by 4, and that is going to give me y is equal to 8 minus 2x over 4. Without simplifying things, we'll keep it as is. And we can graph this. If I was to plug 1 in here for x, then the top part would be 8 minus 2 times 1, which is 8 minus 2, which is going to be 6, divided by 4. And so when x is equal to 1, this whole entire y is going to be equal to 6 over 4, or 3 over 2, which is a little bit over 1. We could probably put it, it's 1.5, so let's put it right here. And if I plugged in 2, that'd be 8 minus 2 times 2, which is 8 minus 4. That's going to be 4 over 4, which is 1. And if I plugged in 3, then that's going to put me at 2 over 4, ultimately, and that's about 1/2, so it'll go right here. And so we can actually graph this first linear equation like this, and it doesn't go through all the points. I'll actually, for the sake of not confusing anyone, I know everything's not drawn perfectly, but this one right here is going to be y is equal to 8 minus 2x over 4, or over 4, or in other words, this one right here. And now I'm not going to do that for the next equation. I'm just going to draw it out, but essentially it's going to look a little bit like this. And its linear equation, when we solve for y, is going to be y is equal to 6 minus 3x over -2. You can pull that negative out right here. And if we plug in 3 to this equation, we're going to get 6 minus 3 times 3 was 6 minus 9. That's going to be a -3 over 2, or it's going to be a -3 over 2, but we have this negative sign here, so that cancels it out. So it's going to be 3 over 2, which is 1/2. And that's going to put 3 right here. And then 1's going to be somewhere down here. And this equation that we have right here, this is going to be a decent line. This is what this equation is. And this is just another way of writing, we just solve for y here. So we have our 2 equations plotted. So these are 2 linear equations. We have a system of them. A system is just 1 or more linear equations. We have 2 unknown variables, so we have x and y. And we can actually solve for the x and y's that make this system true, such that if I plug in x and y here, I'm gonna x and y here, I'm gonna get 8. If I plug in x and y here, I'm gonna get 6, and that's what it means to solve. And so when we solve for a system of linear equations, we are actually solving for where these two lines for these linear equations intersect. And so we solve for this. So we solve for this intersection. So when you solve a system of linear equations, you're solving for the variables that not only balance each of these linear equations, but what that does is it actually solves where the two lines for the linear equations intersect. And so we're actually going to stay with this example, and we're going to go through some methods on how to actually go about solving these systems of linear equations, and we're going to do that in the next video. All right, so this was our system of linear equations right here, and we showed how this is how they would plot if we plotted them on this is what their lines would look like if we plotted them on the Cartesian coordinate plane. And we said that if we solve for x and y, not only are we balancing these equations, but we're solving for the intersection here. And so I'm going to step through how do we actually go about solving this system right here. And I'm going to use a technique called Gaussian elimination. So it's Gaussian. This right here is a U, Gaussian elimination. Preferably, I would rather say this as it's a method called back substitution. And I'm going to show you what this does. So what we do is we take our equation. We had 2x plus 4y equals 8. I know I don't have it on the screen, but you can double check that that's the case. And so what we do is we create what's called an augmented matrix. And so we're going to have 2 here for the x. This column is going to represent the x section. This column is going to be the y section. And then this line is going to be drawn between this equation and its solution, what it's supposed to equal. And not its solution, what it's supposed to equal. And then the next line is going to be for the next linear equation, 3x minus 2y. And so we have a negative 2y and then a 6 right here. And so what we're going to do is we're going to do some row operations on it with the goal, since this is a 2 by 2 matrix, of having this right here be 0. And what we're going to be left with is this triangular matrix, right, where we can just solve for y right here. We can take y and then plug it into the top equation and then solve for x. And I'm about to show you what all that means. So to do this row operation, this is a 2 by 2 example, so it's very straightforward. I want to set this equal to 0 so that I can start doing some back substitution and showing you what I mean. So I'm going to set row 2 equal to 2 times row 2 minus 3 times row 1. And so why does that work? Well, if I multiply this number by 2, I get 6. That's row 2. It's in row 2. And if I subtract off 3 times this number, which is 6 as well, then this, and I set this equal to it, then it's going to be 0. And so we know that the first row does not change because we're not doing any row operations to it. We're doing it on the second row. And so we know we set this one equal to 0. Now we have to do the same operation to this one here. Now, 2 times negative 2 is going to be negative 4. And we're going to subtract off from that 3 times 4, because 4 is in the first row. So negative 4 minus 3 times 4 is 12. So negative 4 minus 12 is going to give us a negative 16. And we're going to do the same thing to the other side as well. And so 2 times 6 is going to be 12, minus 3 times 8 is going to be 24. So 12 minus 24 is going to be a negative 12. And right now, we can actually view this as this. 2x plus 4y is equal to 8. And then we have negative 16y is equal to negative 12. And so we can solve for y right here. So y is going to be equal to 12 over 16, which is, if we simplify this, is going to be equal to 3 over 4. And if we plug that in up here, we are going to have, actually, let's just stay right here so we have everything here. This is going to be 2 times x plus 4 times 3 over 4, because we're back substituting in y. It's equal to 8. That's going to be 2x plus 4's cancel out, which is 3 equal to 8. We subtract 3 off, and then we solve for x, which is 5 over 2. And so we are left with the fact that x is going to be equal to 5 over 2 and y is going to be equal to 3 over 4. And if you look at this, I said that the solution is going to be where the two lines intersect. If 3 is right here, all right, this is 3. So this is 2 and this is 3. 5 over 2 is 2.5. So 2.5 is going to be about right here. And y is 3 over 4. And so 3 over 4 is probably about right here. And if you look at that, I know everything's not drawn perfectly, but hopefully you can see that this really is where these two lines intersect. And just to prove our work shortly, I'm going to plug these x and y variables into their solutions into 2x plus 4y is equal to 8. And both sides should equal 8. And so this is going to be 2 times 5 over 2 plus 4 times 3 over 4 should give me 8. Well, the 2's cancel out here, so we're left with 5. The 4 cancels out here, and so we're left with 3. And as you can see, both sides do equal 8. And so I encourage you to try this on the other linear equation, plugging in 5 over 2 and 3 over 4 for x and y respectively into 3x minus 2y is equal to 6 to see that both sides will equal to 6. And you can see, you can definitely reason about the fact that this is where the two lines intersect. And that's how you use Gaussian elimination, I like to say back substitution, to be able to solve a system of linear equations where you have two unknowns and two linear equations. So we've learned what a system of linear equations is. We've learned one method called Gaussian elimination or back substitution for solving a system of linear equations. I want to go through another method, and it's actually called Cramer's rule. So I'm going to write Cramer's rule. And we're going to use it to solve our system that we've stuck with throughout this series of videos. We have 2x plus 4y is equal to 8, and we have 3x minus 2y is equal to 6. And so hopefully you can see that that is an 8. And what Cramer's rule says is that the solution to x is going to be equal to this. It's going to be equal to the determinant of our matrix here, 2, 4, because we can build this matrix A, which is 2, 4, 3, and negative 2, right? This is our matrix A that represents these coefficients. And it's going to be the determinant of this matrix with the solutions right here, or this solution column here, plugged into the x column. And so we're going to replace this column with 8 and 6 right here to get dx. And then we're going to divide it by d. All right, so x is going to be equal to dx divided by d, where d is the determinant of a with nothing. We're not plugging anything in. It's just going to be the determinant of a. And so likewise, the y is going to be equal to the determinant of a with this column, these numbers right here, plugged in and replacing the y column, and then divided by d. And so that's Cramer's rule. And so let's get to solving for d. So d, right, is going to be equal to the determinant of a. And a is a 2 by 2 matrix, so we can do this pretty straightforward. We just take, it's going to be 2 times negative 2 minus 3 times 4. And so 3 times 4 is 12, but we're going to have negative 4 minus 12, and that's going to be equal to negative 16. So let's go ahead and put negative 16 in here. Alrighty, and then let's solve for dx and dy. And so dx and dy. So our solutions, we're supposed to have these equations equal 8 and 6. They're not our solutions. It's what these equations are supposed to equal. But we're going to plug them in for the x column. So put 8 and 6 here, and then keep y the same. And let's solve for the determinant of this matrix. And so we want the determinant here. I'm going to draw bars around it. And it's pretty straightforward. You know, multiply these two together. It's going to give me negative 16. Subtract off these. It's going to be minus 24. And then we're left with negative 16 minus 24 is going to give me negative 40. And so let's plug in dx. It's going to be negative 40. And if we simplify this further, we can see that, you know, these negatives cancel out, and then we actually can simplify this down. You know, if we divide by 8 right here on both numerator and denominator, we can get down to 5 over 2 for x, which you know is the exact same answer we got using back substitution. And so that's some reassurance. Now let's do dy. And so I'm going to do dy right here. Nope, we're doing 3. Remember, this is dx. 3, you know, the next one we're going to do is dy. And dy, well, this is going to be equal to, we're going to plug in 8 and 6 where the y column is and take the determinant of this matrix. And that's going to be, you know, 12 minus 24, and that's going to be negative 12. And let's plug that in for our dy. Negative 12. Negatives cancel out. We reduce it by dividing the numerator and denominator by 4, and that's going to give me 3 on the top and then 4 on the bottom. And this is our x and y that we got in the previous video, which we showed actually is a solution to the system of linear equations. It does make sense. And we get the same thing using Cramer's rule. It's just a different way. We're going to take our results that we have right here, and we're just going to plug them in. To solve for x, we just take it to create our dx matrix. We're just going to take these results, plug it in, replace the x column right here of our A matrix with these numbers, and then calculate the determinant of the matrix, and then plug that in here. And it's very creative. You know, it's not obvious. This is not something you kind of wonder, how would you invent it? There's a lot of videos on how Cramer's rule actually came about that I encourage you to go watch. But nonetheless, this is how you actually solve a system of linear equations in practice using Cramer's rule. So in this video, I want to show you how to compute the eigenvalues of a 2x2 matrix, specifically this matrix that I have right here. It's a 2x2 matrix, and I won't go into the theory as to why we do it this way, but you know, if you take some of our paid courses, or you go online, you can look at it as well. There is a reason why we do it this way. But first and foremost, let's start off by saying this. When we solve for eigenvalues and eigenvectors, we're solving this equation where we're trying to figure out the v's right here. These represent our eigenvectors, and the lambda here is our eigenvalue. And so we're trying to find the eigenvectors, these vectors, such that if we take A and we multiply it by V, we are just going to scale it up or scale it, you know, down by a particular value lambda. And so if I multiply A by V, I may take V, right, and I may scale it up, you know, by 2, so it's 2V. In that case, the eigenvalue is just going to be 2. And so that's essentially what we're solving for here. When we solve for eigenvalues, we're solving for lambda right here. And how we do that is, I'm not going to go into why, but how we do that is we solve for the determinant of this matrix right here. So this right here, this I is the identity matrix, and it's just a matrix of ones along the diagonal. And so I'm going to hop right into it. What we're going to do is we're first going to try to, you know, we're going to take the determinant of everything inside here, which is going to be lambda times I, the identity matrix with ones along the diagonal, minus A, which is 2, 3, 1, 4. Okay, and we want this to be equal to 0. We are going to distribute through lambda, and then we're going to subtract off A. I can do that a little bit neater. Okay, and then this is going to give me this matrix right here. Awesome. And now we can take the determinant of this. And so what we can do is, I'm going to scroll down. When we take the determinant, we're just multiplying the right going diagonal right here and then subtracting off the multiplication of that diagonal as well. And that's going to leave us with this, lambda minus 4. And then subtracting off -1 times -3 is just +3. And we can use our good friend FOIL. You remember FOIL, first outer, inner last. That's going to be lambda squared minus -2 lambda minus 4 lambda is going to be -6 lambda plus 8 minus 3 is going to be 0. And so simplifying this down, we're going to have plus 5 is equal to 0. And this is called our characteristic equation. You'll hear that a lot. And so what we want to do is we want to figure out what are two numbers that when multiplied give you 5, but when added up give you -6. And that is -5 and -1. And that's what's going to solve this. It's lambda minus 5 and then lambda minus 1. And if we solve this, we can see that we have lambda is equal to, these are the solutions to our characteristic equation. And these right here are our eigenvalues. And so that's how you solve for the eigenvalues. Please feel free to go back through that to catch the steps more closely. But what we essentially did is, we noted that this right here is the equation we're trying to solve for both the eigenvalue and the eigenvectors. The eigenvalue is just the scalar for when A is multiplied by V. And then the determinant here is, we're going to take the determinant of this inner matrix right here. And what we do is we set everything up. We know what the identity matrix is. We know what that is now. We finally get this. We take the determinant of this. It winds up giving us this characteristic equation, and we solve for the lambdas for this binomial equation or the characteristic equation. And then we come out with 1 and 5, which are our eigenvalues. Now, in the next video, I'm going to show you how to calculate the eigenvectors of this matrix. In this video, I want to show you how to compute the eigenvectors of this matrix. And so to compute the eigenvectors, we're actually going to solve for this equation. We're actually going to solve this equation right here. And so it's a little bit different than the eigenvalues where we solve for the determinant of this matrix equal to 0. We're trying to find this vector v right here that makes this equal to 0. We won't go into the theory as to why that's the case, but we have a paid course on this that will explain that to you, as well as there are other resources on the internet that will explain it to you as well. And so let's start by, what we first do is we have to plug in each of our eigenvalues into this equation right here and solve. So let's start with lambda is equal to 1. And so if we plug lambda is equal to 1 into here, what's going to happen is when we multiply lambda's 1 times the identity matrix, it's just going to give you the identity matrix back. And so this is going to be this right here. And then we're going to subtract off A. All right. And then we know we have all this times V equals 0. And when we subtract off these two matrices component by component, we're going to get this matrix right here, -1, -3, -1, -3 times V is equal to 0. And so right here, what you're trying to do is you're trying to solve, you're trying to get this matrix into a reduced form such that you can solve this matrix equation. So that, this matrix right here multiplied by this vector is going to give you the 0 vector. So we call this vector over here the 0 vector. And so I figured that, a good way to do that, as long as you keep that train of thought, you're trying to reduce it into a form such that it's very easy to solve for V1 and V2. I realize I can do that by doing this, right? I can subtract off row 2 by row 1, and I can put this matrix and set row 2 equal to that. I can put this matrix into this form, and that multiplied by V1, V2 is equal to 0. And then if I multiply this by -1, distribute that through, then these are all positive. And now, if I can write this equation out like this matrix vector product out like this, right? So what's going to happen if I multiply this matrix by this vector is that I'm going to take this row vector and multiply it by the vector right here, take the dot product of it, take the dot product of this row vector with this vector and get the 0 vector. And what that's going to look like is it's going to be 3 times V1, it's going to be V1 plus 3 times V2. Which is equal to the 0 vector. I can then subtract off V2 from both sides, and that's going to be -3 V2 from both sides. And what this is saying is that the first component, here you go, the first component of this vector, v1, is going to be equal to -3 times v2. That means you give me any v2, any number, it could be v2 equal to 6. This first component right here is going to be -3 times that, so it would be -18 in this case. But how do we write this as an eigenvector? Well, what we can say is that the eigenvector for lambda equal to 1, this is how we would write it, is going to be some constant c, right? Where we can imagine, let's imagine v2 was c. Well, if v2 was c, and this is one way you could think about it, we know that v1 is going to be -3 times that, and then v2 is just going to be 1. It'd just be itself, right? Because if we have v2, whatever number v2 was, this component is right here, and we left it outside of the vector and we multiplied our vector by it, v1 is going to be -3 times that, and v2 is just going to be itself, right? And so we can just replace this with any old constant, because you can put any old constant in here and it'll still be a vector. And as long as it shows that v1, the first component, is -3 times the constant, and v2 is the constant, then we have it. And so this is our first eigenvector. Now, let's go down and let's solve for lambda is equal to 5. So I won't step through, lambda I minus a or anything like that. I'll just go through and create lambda I minus a. Lambda I minus a, this is going to be equal to, 3 minus 3, -1, and 1. And we want to solve this equation. Well, I can put it into reduced form by doing these two operations, right? And this is going to give me everything on the top stays the same, but the bottom cancels out. And next, I'm going to do a second row operation where I'm going to set row 1 equal to 1/3 times row 1, where I'm just going to multiply it by 1/3. I didn't have to write this out explicitly like this. And so here we go. And so this is actually very straightforward. I mean, if you think about it, right, this top row vector dotted with this vector right here equal to 0 is just going to be, let me give myself a little more space. It's going to be v1 minus v2 is equal to 0. We can add v2 over. That's going to be just like this. v1 and v2 are always equal to each other. And so the eigenvector for lambda equal to 5, or eigenvalue equal to 5, is going to be some constant, where this constant could literally be v2, just like we did in the last example, times this vector. We know that v1 is going to be exactly what v2 is, and v2 is going to be exactly what v2 is, obviously. And so this is our second eigenvector. And so E1 right here is our eigenvector for lambda equal 1, and E5 is our eigenvector for lambda equals 5. This constant right here means that any constant times this vector is going to be an eigenvector of this matrix for lambda equal 5, or for eigenvalue equal 5. Same thing here. If I plugged in c is equal to 206 and multiplied it by this vector, that resulting vector would still be an eigenvector for eigenvalue equal to 1. So we've talked about how to compute the eigenvalues of our matrix A, a 2x2 matrix. We've talked about how to compute the eigenvectors of that matrix. In this video, I want to go over how to diagonalize this matrix. And so diagonalization is a way of decomposing our matrix. And you can see here, like if we have our matrix A, we're going to decompose it into 3 different matrices, P, D, and P inverse, where, going this way, P is our matrix of eigenvectors, and we're going to show you what that looks like. D, is a matrix with our eigenvalues on the diagonal, and everything else is 0. It's similar to the identity matrix, where the diagonals are only 1 and everything else is 0, except our diagonals are our eigenvalues. And then P inverse is the inverse of our matrix P, simply. And what this is saying is that if I take P, I multiply it by D, and then I take the resulting matrix of PD and I multiply it by P inverse, I should get A back. And that should seem pretty cool to you. it's essentially called the matrix chain multiplication. The matrix chain multiplication of PD and P inverse will give you A. So it's a decomposition of the matrix A. And so let's go ahead and build these matrices using our example, what we know now. This is our A. We know these are our eigenvalues. We know these are eigenvectors. And so what this is saying is that A is going, all right, so P, let's first do P. P is going to be equal to, see, we're going to take each eigenvector and make it a column vector of P. And D is going to be a diagonal matrix of our eigenvalues, with which we need to make sure that the eigenvalue that's in this spot right here matches up with the eigenvector here. And so this is going to be eigenvalue 1, and this can be eigenvalue 5. Remember, those were the respective eigenvectors for those eigenvalues. And then P inverse. Well, we just need to invert P. And a 2 by 2 matrix is very straightforward to invert. We just flip this diagonal. And so this can be 1 and -3. We negate this diagonal, just -1, -1. And then we divide through by the determinant of this matrix right here, which is going to be this diagonal multiply, which is like -3, minus this diagonal right here, which is 1. And so this is going to be -4. I'm going to go ahead and write that in. So it's going to be -4. Leave the negative out here. And if we distribute it through, we're left with -1 over 4, 1 over 4, 1 over 4, and then 3 over 4. And then this right here, you can take P times D, and then take the resulting matrix of that and then multiply it by P inverse and get A. And I'm going to leave it to you as an exercise to do that and prove it to yourself that this actually, the matrix chain multiplication with P times D times P inverse will actually give you A back. And so just to confirm your knowledge, please go ahead and do that. So in this video, I want to talk about what a linear transformation is. So a linear formation is essentially every linear transformation. You can think of a linear transformation as a function. And so we're going to write it as a function t that's going to take in two vectors in this case, or one or more vectors. And these are the rules for a linear transformation. It should be that when we take this function, this linear transformation, and we apply it to the sum of two vectors, that's what this is, the sum, we should get the same thing as if we had taken the transformation of each vector individually and then added them up separately. Another rule is that the transformation of a single vector, of a scaled version of a vector, so if we scale the vector and then take the transformation, this should be the same thing as taking the transformation and then scaling it up. And then finally, this sort of follows from these two, is that the transformation of a constant times v plus another constant, let's say c2 times w, okay, should be equal to c1 times the transformation of v plus c2 times the transformation of w. And that follows from the first two that I listed. So those are the rules for a linear transformation. And so to go a little bit further in depth, let's talk about I think a really straightforward example. And first, let's think of transformations. You'll commonly see them represented as mappings, and they're functions. They're functions or mappings. And we're going to talk about a transformation that takes a vector that's an R2. That's a two-dimensional vector. That's how we show that this vector is two-dimensional. It means it has, two components. 1 is a vector in R2, and it maps any vector in R2 down to R1, which is just a real number. Like it'll take a vector 1, 1 and map it down into the number 2 or something like that. And so scrolling down a little bit, this transformation is going to consist of, it's going to be a function that if you give me a vector, right, v1 and v2, okay, you give me a two-dimensional vector, it's just going to output v1 plus v2. Very simply, it's just going to add up the components. And so this transformation applied to 1, 2 is going to give me the number 3, because 1 plus 2 is 3. And so why is this a linear transformation? Well, it's linear because, first, if we take the transformation, right, of the sum of two vectors, let's have two vectors. We have v1, v2 plus w1, w2. This is going to be the same thing as if we had taken the transformation of v1, v2, and then added it to the transformation of w1 and w2. And why is this the case? Well, this is going to be the transformation of the sum of these two vectors is just going to be v1, right? After we add these vectors up and then add their components afterwards, it's going to be v1 plus w1, right? Plus v2 plus w2, okay? And that's going to be equal to v1 plus v2 plus w1 plus w2, right? Because addition knows no groupings, right? These two sides, you can take away the parentheses, right, and get the same answer just by the rules of addition. And they are going to be the same thing as each other. No matter how and what order we add these numbers up, no matter what order we add up these components, they're going to be the same. And so that's the first rule. And then the second rule, we have that the transformation of C times, let's say, a vector v1 and v2 is going to be equal to C times the transformation of v1 and v2. Let me write this a little bit neater. And that makes sense because we know we're just adding up the components. This is going to be, we're going to first multiply each one by C and then add it up. And this side right here is just going to be C times v1 plus C times v2, which is going to be, and this side right here is going to be C times v1 plus v2. Since we can distribute through the constant, we're left with c1 plus c times v1 plus c times v2. And both those sides are the same. And so this right here, where we just simply add up the components, is a linear transformation. And this is the reason why. And the third one follows from the first two. And I challenge you to use the same logic of having these general components and going through it to be able to prove it to yourself. 1, 2, 3, starting. So in this video, I want to go through an example of a linear transformation and then relate it back to what we learned about eigenvalues and eigenvectors and solving that equation to get those. So this right here, the transformation of a vector, if I define it to be a matrix A times that vector, this is a linear transformation. Or say it's linear. I'm going to make it a comment. This is linear. So why is it linear? And so if we look at rule number 1, right? If we think about it, this transformation A, this matrix times any vector, is going to be, let's say we're going to take A and we're going to multiply it by A plus A times V plus W. All right. Well, we know we should get A V plus A W if it's linear, and we do, and the reason is that and we haven't talked about this before, but the matrix multiplication here with these vectors, it's distributive, and so that is why it is linear. Rule number 2 is, if it's linear, we know we should be able to we'll take the matrix vector product between A and C times V. And this should be the same thing as C times A times V. And this is true because for any constant, we can just take it out algebraically, and we still get the same result. And so for number 3, let's look at rule number 3. So we should have that A times C times V plus C2 times W. Okay, this should be equal to A times C1 times V plus A times C2 times W. And we know that it's distributive, and so this makes sense, right? And we also know that we can just factor these out. And so we have C1 times A times V plus C2 A times W, and we are good to go. And if you review your the original rule number 3 from the previous video, then you'll see that this is true. And so let's talk about the eigenvector equation. And so the eigen equation is such, right? A times V is equal to lambda times V, right? Where this right here, this is going to be our eigenvalue, and this right here, V is on both sides, is our eigenvector. And A, right, we now know is a transformation matrix. That's what that says. Sorry if that's not clear. That's a transformation matrix. That's what we call it. If we have a transformation where we're saying that it's A times a vector like we're doing above, that matrix is what we call a transformation matrix. And so what we're trying to find when we're solving for the eigenvalues and eigenvectors is we're trying to we have a matrix A, and we're trying to find the that when we're trying to find the vectors, okay, V, that when transformed by A, when we apply the transformation of A to those vectors, they only get scaled up or potentially, flipped or scaled down, however you think it, by their corresponding eigenvalue. And so if lambda, like I said before, is equal to 2, then that means if A times V, it's just going to be equal to 2 times V. And so if this is V, this is going to be 2 times V or A times V. And so that is what you're solving for in the eigenequation. So that's an example of a linear transformation, representing it as a matrix vector product and relating it back to what we learned about eigenvalues and eigenvectors. So in this video, I want to go over what a subspace is, what a basis of a subspace is, and also what the span of a subspace is. And so let's talk about what a subspace is. First, let's think of, or more so a linear subspace. And so I'm going to draw a set, okay, and I'm going to say that this set is the set of all two-dimensional vectors. Every two-dimensional vector you can think of is in this set. And I'm going to draw a subset of it, and I'm going to name it V. Call it V. V is, I'm going to say R2 is our complete vector space of all two-dimensional vectors, and V is a subspace of it, or a subset of that space. And so what makes it linear? And so, well, one thing that has to happen is that it has to contain the zero vector. So it contains zero vector. So that's a vector where every single entry is 0. For any vector x, so for all vectors x, that's what this means right here, for all vectors x that are in V, right? This right here, this little symbol that I'm about to write, means that they're a member of V. For all of them, if I were to scale them up by any constant, scale them down, or scale them by any constant c, that resulting vector is still a member of V. So if x is right here, here's the point x, and I scale it up, c times x should still be in V. We shouldn't scale up x and then suddenly we're out here. That would be a no-no. We do not do that. And so that's one law. The other one is that if I have two vectors a and b in V, a plus b must also be a member of V. And so if I have these two vectors, I add them together, I should land a plus b should be in V as well. And so that's a linear subspace. Now let's move on to what a basis of a linear subspace is. So a basis of subspace. Okay, so first off, what is a basis? So a basis for a subspace is going to be a set of vectors. So we're going to call it B is our basis, is a set of vectors, b1, b2, all the way up to bn, okay, such that all of them are linearly independent. I'm about to explain to you what this is. Okay, linear independent just means that I cannot grab any vector in here. Like just pick a random vector, any of these vectors, pick any of them, and like let's say b1. I should, if these sets of vectors are linear independent, this right here should hold for all of them. I should not be able to write any of them as a linear combination of the others, right? This right here should not be possible at all. That should not be possible. And what that means is, like, you could think of it as it's literally a linear combination. Plug any real number into these C's. What if I should not be able to solve this at all? B should be like in an island of its own. B1 should be in an island of its own. And every vector should not be able to be represented as a linear combination of the other vectors in the set B for it to be a valid basis. And what this means is that any vector, so if I have B is a basis for V, this means that any vector V for all V in the set V, little v and V, right? I can say this, that little v, I'm going to say Vi, is going to be equal to C1 times this one, this basis vector, times this basis vector, and so on. I can write every single vector in the set V, the subspace here, every single one can be written as a linear combination of the basis vectors. And if these sets of vectors are linearly independent and any vector in V can be written as a linear combination of them, then this is a basis for that subspace. And so moving on to a span of subspace, okay, it's just all possible linear combinations of B. So you see, like if you made you think of like C1 here, we have C1 times B1, C2 times B2. Plug in every single number you can possibly, an infinite amount of real numbers into all of these different C's. You can imagine that would be a ton. But all of the resulting vectors from plugging in all these like different C's, all possible linear combinations of them, is going to span all of V. It's going to fully fill this in. And so like if you were to simulate this on a computer and you were to plot the points, right, you would see how over time every single linear combination would eventually fill in V, and then it would get to the point where, you know, the points were so dense that you had literally mapped out every single possible vector in V, and that is the span of a subspace. The span of the subspace is all possible linear combinations of their basis vectors. It's every single vector you could possibly create in this subspace. And so that's a linear subspace. That's what a basis is. That's what it means for it to be a basis of what it means to be a basis of a subspace. And this is what it means to have a span. It's all possible linear combinations of the basis vectors of a subspace.